So, good afternoon, everyone. Welcome to the UFABC Colloquium of Physics. So, today we have the pleasure of having Professor Ferruccio Feruglio from University of Padova. He graduated in what is it? In Italy, and then he did his master's in Sisa in Trieste and did his PhD in the University of Univ under the supervision of Professor Gatto. Did a lot of postdocs, and then he's full professor in Padova since 2002, and he will be talking to us about the modular flavor symmetries, which is his last influential paper among a lot of ideas. So please, thank you for giving us a talk.
Thank you very much for the kind invitation, for giving me the possibility of presenting this talk. I will talk about the modular invariance approach to the flavor puzzle. And so let me start by presenting this flavor puzzle. These pictures summarize the building blocks of particle physics. And the focus on this talk will be on the matter components, which comes in 3 generations having exactly the same quantum numbers. You see these 3 columns here. Each generation comprises quarks that experience both strong and electroweak interactions, and leptons which only have weak interactions, and they come in 4 different charge sectors. And it turns out that to describe completely this sector of particle physics, beside the gauge couplings, we need up to 23 free parameters that are the masses of these 12 particles. Then we have 3 mixing angles for the quark sector and 3 mixing angles for the lepton sector, describing the possible transition between the first and the second, the first and the third, and the second and the third generation. And then up to 5 independent phases that are attached to CP violation. Now, in this logarithmic plot, you see the masses of the 3 generations. On the right here, you see the charge fermions. And in particular, you see that there is a clear hierarchy among the masses of the different generation, with the first one, which is lighter, the second one is in the middle, and the third one is the heaviest one. At the same time, within the same generation, the particles are close in mass. The largest spread is in the third generation by a factor of about 100. Neutrinos, which are neutral particles, instead have a completely different behavior, because you see that they are much lighter than the charge fermions. There is a gap between the top quark, which is the heaviest fermion, and neutrinos, which is of about 12 order of magnitudes. And moreover, so far we have no evidence for a mass hierarchy among the neutrino generations. All these properties are encoded in 4 mass matrices for the up, down, electron and neutrino sectors. These are matrices in a generation space. And in particular, the mixing and the mixing angles arise from the misalignments among these matrices. For instance, in the quark sector, we have the Kabibbo-Kobayashi-Maskawa matrix, the mixing matrix, that quantify the misalignment between the up type quark mass matrix and the down mass matrix. And this CKM matrix is a unitary matrix that can be parameterized in terms of 3 angles and 1 phase. And similarly, in the lepton sector, we have another mixing matrix, the Pontecorvo-Maki-Nakagawa-Sakata matrix, that is parameterized in terms of 3 angles and up to 3 phases. And if we compare the Kabibbo-Kobayashi-Maskawa mixing matrix of the quark sector with the one in the lepton sector, you see that they are completely different. The Kabibbo-Kobayashi-Maskawa matrix is a nearly diagonal matrix with small off-diagonal entries, which means that the mixing angles are small. The largest one is the one describing the mixing between the first and the second generation. Instead, in the case of the lepton mixing, we have all entries of about the same size, apart perhaps for the E3 entry, this one which is the smallest one, which means that all the mixing angles are large. So these are different features in the quark sector and in the lepton sector as far as the mixing is concerned. Finally, we have another parameter, which is the theta bar parameter. This is a CP violating quantity, which is a combination of the so-called topological QCD angle, the angle that controls this GG tilde combination of the gluons, and the phase of the determinant of the quark mass matrix. And from the bound that we have on the electric dipole moment of the neutron, that is a CP violating quantity, we have a severe bound on this theta bar parameter that should be smaller than 10 to the minus 10, while at the same size, at the same time, the phase that enter the quark mass matrices, that is the Kabibbo-Kobayashi-Maskawa phase, also arising from the same mass matrices, is known to be of order 1. So this difference between this CKM phase and this theta bar parameter is known as the strong CP problem. So now the question is how we can try to put this information together. Is there a principle or any rationale that can be discovered behind this data that can help us to quantitatively describe these all these parameters in terms of a smaller set of data, or we should be happy with this description, which uses so many parameters. The first hint comes from neutrino masses, because we have a nice explanation of the smallness of neutrino masses if we regard the standard model as the lowest order of an effective field theory. We know that the standard model is Lagrangian, assembles all gauge invariant operator whose dimension is less or equal to 4. And this requirement comes from renormalizability. And if we relax this requirement and we add to this Lagrangian also higher dimensional gauge invariant operators of dimension 5, 6, etc., that comes suppressed by some new scale lambda for dimensional reason, then you see that if this scale lambda is very large, this explains why all this theory is dominated by the lowest order part, the lowest order operators, okay? Now, if we consider the dimension 5 operator, which is the most relevant one besides the one in the standard model, up to flavor combination, we have a unique operator which is made up of two X doublets and two lepton doublets. And so is an operator that violates the combination B, the baryon number, minus L, the lepton number, by 2 units. No, it has two lepton fields and no baryonic component. And if we make this operator more explicit, we see that it contains in the lepton fields a neutrino bilinear, so it provides a mass term for neutrinos. However, this mass term comes with a suppression by a factor V. V is the electroweak scale over this scale lambda. And so you see, if this factor V over lambda is very small because this scale lambda is very large, then this mass is suppressed compared to the charge fermion masses, which are only proportional to the electroweak scale and has no this suppression factor. Okay, so this is a very nice explanation. The neutrino masses are small because this scale lambda, this new scale that enter our effective field theory, is very large. How large? To fit what we know today about neutrino masses, this scale lambda should be very large, about 10 to the 14 or 10 to the 15 GeV. So a huge scale, which, by the way, is very close to the grand unification scale, which is close to 10 to the 16 GeV, which is very relevant in particle physics because is the scale at which strong and electroweak gauge interactions can unify. So we have this nice explanation, and moreover, you see that when this scale lambda becomes really extremely large, let's send this scale to infinity, neutrinos become massless, and these restore a symmetry, B minus L. And so you see how the concept of symmetry enters the game of fermion masses. A small mass can see as a small symmetry breaking of a certain scale, in this case, the difference between the baryon and the lepton number. And it is undeniable that symmetries played an important fundamental role in describing the fundamental interaction and in helping us to discover the principles behind the fundamental interaction. And so it is natural to try to adopt a strategy of flavor symmetry, so a symmetry that acts in generation space, to try to explain the mystery of the fermion masses and mixing angle. Let me give you an example. Suppose that we assign to each particle, to each fermion, a charge. So we have a symmetry, which in this case is a U1, is an abelian symmetry, is a continuous symmetry. Each field possesses a charge. And if we assign charges in such a way that the only vanishes combination is the one concerning the third generation, then we end up with a lepton. In this case, I make the example of leptons, a lepton mass matrix in which all entries are 0, because they are not compatible with the symmetry, but the 3-3 entry. So we have a nice prediction. This simple exercise predicts a non-vanishing tau mass. Tau is the third generation charged lepton, whereas the electron and the muon remain massless in this particular limit of exact symmetry. So this shows you at the same time that an approach based on symmetry can be useful to have a first-order approximation of the data, while at the same time we need corrections to also account, in this case, for the electron and the muon that we know are massive, even though their masses are much smaller than the tau one. And this correction can come as a symmetry breaking effect. So we can have a symmetry which in the exact limit provides massless electron and muon, and now turning on symmetry breaking effects can give masses to also the light generations. And this shows the importance of symmetry breaking. In general, the symmetry breaking sector consists of a set of order parameters. These order parameters are usually vacuum expectation values of gauge invariant scalar fields that are charged under the flavor group. This can be made dimensionless by counting these vevs in terms of an appropriate unit. And so we can expand a generic mass matrix in powers of the symmetry breaking parameters. The first term in this expansion is the symmetric limit. In the previous example is this matrix here. And then to account also, to achieve a realistic prediction, we should turn on also the next term in this expansion, which are linear terms in these tau symmetry breaking parameters or quadratic terms, and so on. So you can see what are the problems of this type of description. First of all, a realistic mass matrix needs several of these corrections, and so this brings several free parameters in the game. Moreover, also we need to adjust carefully both the size and also the orientation in flavor space of these symmetry breaking terms. And this problem is known as the vacuum alignment problem in the symmetry breaking sector. So people try a lot, tried hard. There are a huge number of models using both continuous and discrete flavor symmetry, abelian, non-abelian, global or local. But from this exercise, so far, no baseline model has emerged. So let me summarize the usual path. Usually we choose a flavor group. We assign quarks and lepton to multiplets of this flavor group. And then in the end, we look for some symmetry breaking sector, and we try to adjust our symmetry breaking parameters in order to make the description realistic. You see that in this approach, the crucial sector, the symmetry breaking sector, is relegated to the very last step. But in this talk, I would like to show you that we can reverse the logic and start from a symmetry breaking sector that can be either mathematically or physically motivated, and go back and try to try to see what is the symmetry which is supported by this symmetry breaking sector. Let me give you a simple example. So just to give a name, I call a moduli space the space that parameterize all possible symmetry breaking parameters. So indeed, all possible vacua of the theory, since these symmetry breaking parameters are nothing but vacuum expectation value. And suppose that from the very beginning, I know that this moduli space consists of the lines of the plane that pass through the origin. Okay. How can I parameterize this moduli space? Well, I can draw a circle that is a center at the origin. And if I pick up a point on this circle, this describes a lines that pass through the origin. However, you see immediately that this description is not unique. This description is redundant because 2 points sitting at the opposite sides of the circle represent exactly the same line. And so you have a symmetry in this description. It is a symmetry which is related to the redundance of the description. It is a simple parity symmetry in this case, that is a gauge symmetry because related to a redundancy in the description of the physical degrees of freedom. This is like in electrodynamics, in which two different electromagnetic fields that are related by a gauge transformation describe exactly the same electric and magnetic field. And we have to do with a gauge symmetry because this gauge transformation is nothing but a U1 local gauge transformation. Okay. And now, exactly as we do in electrodynamics, that with a choice of gauge which we can restrict this electromagnetic field, also in this case with the gauge choice we can restrict this description, which is redundant, to half of the circle, which represent the so-called fundamental domain. Let me give you a less trivial example, bringing me to the topic of modular invariance. If we think to string theory, which is defined in 10 dimensions, to get a realistic description of our 4-dimensional spacetime, we need to compactify 6 dimensions. The simplest compactification is on 3 copies of a torus. So consider 2 extra dimensions that are compactified on a torus. A torus can be represented as a lattice in which we fix a basis. In this case, these 2 vectors or complex numbers, omega1 and omega2. And the relation with the torus is easily seen if we identify the opposite side of a unit cell. First, we glue these 2 sides and we obtain a cylinder. And then if we glue the opposite edges of the cylinder, we obtain the torus. Okay. And up to rotation, rigid rotation, and dilation, a torus can be parameterized in terms of a complex number with a positive imaginary part, which is the ratio between these 2 base vectors. However, as in the previous example, you realize very easily that this description is very redundant, because there is no unique base on the lattice. We can change the base and still describe exactly the same lattice, and so the same torus. And the general change of bases in the lattice is reflected on this modular parameter tau as a linear fractional transformation of this type, where a, b, c, d are integers, and the determinant of their matrix is equal to 1. So these kind of matrices build up what is known as the modular group. So the modular group is, if you wish, the gauge group, which is related to the redundancy attached to this description of a torus that physically is related to the compactification of two extra dimensions and as can arise in string theory. Just to say a few words on this group, this is a discrete but infinite group. The group is generated by combining these two elements, S and T, okay? And precisely as we did before in the simplest example, by means of a modular transformation, instead of working in the full upper half of the complex plane, we can work on the fundamental domain, which is this strip here, okay? And also, I would like to notice that there are three special points in this fundamental region that are fixed under a transformation, under particular transformation of the modular group. For instance, this point here, tau equal to I, is invariant under the S transformation. S acts on tau as an inversion, and also is left invariant under S square. So it is invariant under a Z4 group, which is a finite group generated by the element S. And similarly, for instance, this corner here is left invariant by other two transformations, so enjoys a residual Z2 cross Z2 symmetry, and also this point here at infinity along the imaginary axis is also left invariant by a discrete symmetry. Okay. Similarly, we can also introduce the concept of CP, and we have essentially a unique way to define CP in this plane. CP is the transformation that sends tau to minus tau complex conjugate up to modular transformation. And from this transformation, you can realize that there are regions in this fundamental domain that are left invariant under CP. For instance, the imaginary axis is left invariant by this transformation, but also these other lines, which are the border of the fundamental region, are left invariant. Okay, now we have all the elements to see how it is possible to build a modular invariant theory. Maybe this could be also a moment to stop if there is if there are questions, if there is any comment, I can make a stop. I don't know if you are able to put questions with this system. If you are able, please do so.
Okay, any questions? Yeah, I don't see any, so please continue.
Okay, so I go on and I show you how it is possible to build a modular invariant theory. In the supersymmetric case, it is simpler. You don't need to know anything about supersymmetry. I will tell you what are the ingredients that enter, in particular, a supersymmetric construction. So in modular invariant theories, this modular parameter tau is promoted to a field. So we have a field. You can think of a scalar field that transform in this way under the modular group. And then we have our matter fields, the quarks and leptons. and we should decide how these fields transform under a modular transformation. First of all, they transform, as usual, with a unitary transformation of the modular group. With one comment that the modular group is very big, is too big, is a non-compact group technically. So as a non-compact group, it does not admit a unitary representation. And so here, instead of having a unitary representation of the full modular group, we have a unitary representation of a finite copy of the modular group. And it turns out that there are infinite such finite copies that are labeled by an integer, which is the level of the finite modular group. Okay. So here we have a unitary representation of a finite modular group, and the first few finite modular groups are very small groups, indeed are permutation groups that are the isometry groups of the 5 Platonic solids. Okay. But most importantly, on top of this unitary representation, we have also here a prefactor that depends both on the modular transformation through the coefficients C and D, on the modulus tau itself, and is characterized by a real number, which is the weight of the representation. So a representation for a quark or for a lepton field has both a level and a weight. Okay. And this is the way in which fermion masses look like in a supersymmetric theory. They are essentially Yukawa couplings, Yukawa couplings that are holomorphic function of the modulus tau. Here is the ingredient of supersymmetry entering, so this Yukawa coupling depends only on tau and not on tau bar. The dependence on tau bar can come through wave function renormalization, meaning the transformation that we need to put the kinetic terms of quarks and leptons in canonical form. If we ignore this transformation, essentially we can think to mass matrices as proportional to the Yukawa coupling. And now modular invariance heavily constrains this Yukawa coupling, because this Yukawa coupling should transform in a certain way under modular transformation with a representation of the finite modular group and with a certain weight. And the object function of tau of this type are called modular form of level n and weight k. And the most important property of these objects, of these modular forms, is that they form a linear space of finite dimension, which means that if you fix the level, the finite modular group, and if you fix the weight, there are only finitely many modular forms that can satisfy this relation. Let me give you an example. Suppose that we work at level 3 and we assign the neutrinos of the 3 generation to an irreducible triplet of level 3 with weight equal 1. And immediately the constraint of modular invariance force the Yukawa coupling to be modular form of level 3, transforming with the weight 2 to compensate the weight of neutrinos. But if we look to this space of modular forms, there are only 3 linear and level 3, which means that the matrix of Yukawa couplings for neutrinos are completely determined by 3 functions. With this technique, many models, in particular for lepton masses, have been build, they are successful, and they can reproduce the 3 neutrino masses, the 3 mixing angles, and the 3 phases on 9 observables in terms of tau, plus 2 or 3 additional parameters. Okay. However, there is a problem because we have a large freedom in building these models. So we have in the market more than 100 of viable models, differing by the levels, the weights that we can assign, the representation, and so on. Moreover, in this construction, these transformation, these wave function renormalization effects are completely ignored. And these are not very much constrained by modular invariance, and they can correct the information that comes from the of the Yukawa coupling alone. So what we can learn by... So I hope that you have followed so far. So I was telling you that we have many, many models, indeed hundreds of models to describe the lepton sector. And in this picture, you see how these models are distributed in the fundamental region. We have different levels that are colored in a different way. And from this picture, you see that the models are not distributed uniformly, but they are a cluster around some particular point. In particular, if we consider a subset of all these models, which is the subset of CP invariant models, you see that most of the models cluster around tau equal to I. You remember that tau equal to I was the point enjoying the Z4 symmetry. And so imagine that we are very close to this point. We can use another set of coordinates. Instead of using tau, we use this coordinate u that has the property of linearizing the S transformation. So in terms of the new coordinate u, this S acts simply sending u into minus u. So if we are close to I, u is small, and we can expand any mass matrix in powers of u. And you see that if you are sitting at tau equal to I, all of this correction disappears, and we have this term, which is a Z4 symmetric term. And if we now are close, but not sitting exactly at tau equal to I, the theory looks like a Z4 theory with small symmetry breaking terms that are parameterized in terms of u, of the deviation of the distance, if you wish, from the symmetric point. And this conclusion is completely independent on the level we are using, on the weights that we have assigned to leptons in this case, on the representation that we are using, and on the kinetic terms of the theory. So it is a universal property of all modular invariant models that have a tau sitting close to I. Okay. In particular, if we add a single assumption that lepton doublets are in an irreducible triplet of the modular group, then the models fall into 3 classes, and there is one class that, again, for any choice of the level, for any weight, and for any choice of the kinetic terms, successfully reproduce the features of the neutrino sector. In particular, maybe I can remember you that in the neutrino sector, we have a mixing angle, θ12, whose sine square is large, is the solar mixing angle. Sine square of θ23, the atmospheric mixing angle, is also large. θ13 is the reactor mixing angle, instead is a small number, is a number of order a few percent. And then we have two neutrinos that are very close in mass because their square mass difference is very small, and a neutrino which is a little bit far apart, either on the top or on the bottom of this kind of system. Okay. And now this slightly broken Z4 symmetric theory, which is universal for all modular models living close to the point tau equal to I, exactly predicts an atmospheric mixing angle which is large, a solar mixing angle which is large deviates from the maximal mixing angle by a quantity which is the distance of tau from the symmetric point. And finally, the reactor mixing angle is small, is the square of this deviation x. At the same time, two neutrinos are predicted to be close in mass because their splitting is of order x. And a third neutrino is very large. No, its mass is inversely proportional to x, so we fall in the case of normal hierarchy. The third eigenvalue is on the top. And the data are reproduced by deviation which are of order 10%. And I repeat, this behavior is universal for all models that live close to tau equal to I, independently of the details of the theory. And this is the deep reason why, even if we have hundreds of models, most of the models indeed describing neutrino masses and neutrino features are clustered around tau equal to I. Okay, so we have this property of modular invariant models that look universal if you are close to a fixed point. Now, let me come to the last topic of this talk, the strong CP problem. So you might remember that we have this theta bar parameter that was a combination of the topological angle and the phase in the quark mass matrices. If we start from a supersymmetric modular invariant and also CP invariant theory, first of all, the topological angle, which is itself a CP violating parameter, is equal to 0. So imposing CP invariance, theta is equal to 0. And so all the phases in the theory should arise from the spontaneous breaking of CP, so should emerge from a value of this modulus tau that spontaneously break CP. So this physical quantity theta bar now is simply the phase of the determinant of the Yukawa coupling in the quark sector. These Yukawa coupling, as we have seen, are modular forms, and also the determinant, which is a polynomial in the Yukawa couplings, is itself a modular form whose weight can be easily computed. The weight of this determinant is simply the sum of the weights of quarks, right-handed quarks up and down, plus the weight of left-handed quarks, sum over the 3 generations, plus 3 times the sum of the weights in the X sector. But these weights cannot be completely arbitrary in a modular theory because, as we have seen at the beginning, the modular transformations are gauge transformations, so they should be anomaly-free. And in particular, if we have an arbitrary assignment of weights, we can have mixed gauge modular anomalies. So we should look for an assignment of weights that is free from these mixed gauge modular anomalies. And the simplest assignment that respects this property is this one. The sum of the weights in the X sector should be equal to 0, and the weights of the 3 generation of quarks and leptons should be equal to 0 and plus minus some integer k. And this immediately gives a vanishing weight for the determinant of the quark Yukawa coupling. So we conclude that this determinant is a zero-weight modular form, but the only zero-weight modular form is a constant. And since our theory is a CP invariant theory, it should be a real constant. And so with this, we can conclude that this theta bar parameter is equal to 0, at least in the supersymmetric limit. Here is an example in which assigning the quark fields of the 3 generation these particular weights, we can fill the Yukawa coupling in the quark sector, both for the up and down quark sector. These C are a real constant, and E6 and E4 are a particular modular form that are called Eisenstein form of weight 4 and 6. And you see that with a choice of these coefficients C of order 1, we can reproduce quark masses, mixing angle, and also the CKM phase. This is an important thing. We can fit a CKM phase which is of order 1 while having a theta bar parameter which is equal to 0. And we can even extend this description to leptons, also producing a nice parametrization of the lepton sector. And this brings me to the conclusion of my talk. So, modular invariance is a key ingredient of string theory, in particular of realistic string theory compactifications. And from this point of view, it can be analyzed both in the bottom-up approach, which is the approach that I have illustrated in this talk, but also in the top-down approach, is starting directly from string theory as has been worked out by several groups. Perhaps this is one of the key ingredients that can enter to solve the flavor puzzle, who knows. We have seen that close to the fixed point modular invariant models independently on their details show a universal behavior, and in particular close to the fixed point tau equal to I, we can explain lepton masses and mixing angles and predict a normal ordering for neutrinos. The strong CP problem can be solved via spontaneous CP violation. We don't know if we will ever be able to make a precise prediction. Perhaps no, in a pure bottom-up approach. We have 100 and 100 of models, and this multitude of models reminds me about the snowflakes. You know that there was a famous American photographer that took thousands of pictures of snowflakes, showing that despite of the fact that all the snowflakes have six-fold symmetry, there are no two of them that are identical. And so we don't know if we will be able to really find out and single out from so many models the right one. So I conclude here, and I thank you very much for your attention.
Thank you, Ferruccio. So we have time for questions that can be made directly. Just turn on your mic or on the chat if you want. Yes, please, Gustavo.
Hi, thank you for the presentation, Professor. So my question is, if you apply, you can go to SMACT, and all the Wilson coefficients becomes modular form, all the dimensions 6 coefficients.
Sorry, can you repeat? Because my volume is a little bit distorting your, I lower the volume, maybe I understand better the question. Can you repeat?
So if you go to SMACT, all the Wilson coefficients in the EFT become modular forms too?
The Wilson coefficients, well, in principle, in the EFT, this is the dream that indeed, instead of having coefficient, numerical coefficients, we have a function of tau. This would be the dream. But in this modest bottom-up approach, this is not the case. No, the ideal case would be this one, in which we have a single overall factor, and then everything is determined by this function, by this modular form. Unfortunately, this is not the case, because this particular pattern is not realistic. I've been tried to describe the lepton masses, but it fails. It fails by not order of magnitudes, but however, given the precision that we have on the data, this is fails, and so we need more parameters to describe the data. So we should have some Wilson coefficient in our effective field theory, which is not a modular form, but which is a number. So far, this is the situation. And if you go to the quark sector, the situation is even worse, because to describe at the same time quarks and leptons, so far within this approach, you need 14 free parameters. 14 free parameters is less than 23 parameters. So it is already a predictive model. But we have still parameters that are numbers, that are not pure modular forms.
Okay, thank you.
Okay, more questions? Comments? Okay, so maybe I have one. So what do you need to still improve on the predictability of this setting? So about the wave function renormalizations, things like that, how can it be done?
Well, you see, this approach constrains, in particular, Yukawa coupling, especially in the supersymmetric limit. You can even discuss supersymmetry breaking correction. They are small in a large variety of models. So this part here is under control, but suffers still from a large freedom in the bottom-up approach, because this Yukawa coupling can be chosen by selecting different levels, different fermion weights, and so forth. So we have a large freedom in the bottom-up approach, and unfortunately, this freedom probably can only be limited in a top-down approach, in a studying specific string theory compactification, that have the property of being able to fix in a clear way, in an unambiguous way, the level and the weight of all the representation. On top of that, we have also this problem of the correction that comes from the kinetic terms. And so the need to make this kind of transformation to put the kinetic terms in their canonical form. This also can affect the mass matrices. And also these have a large freedom in the bottom-up approach. And the hope is that information from string theory comes and give also information about this particular piece that we have in the game. So far, in a pure bottom-up approach, we can only go close to the fixed point and hope to derive some information which, however, suffers from being imprecise because we have coefficients that we cannot be determined, while the hope is that with the help also of information coming from string theory or from some other kind of principle that can provide more constraint to this construction, we are able to be more predictive.
Okay, thank you. So more questions on the chat and from the students maybe? Okay, so I don't see any, so let's thank the speaker. So thank you for a very clarifying talk. Oh, there is one out there. People are clapping online.
Thank you.
Okay, so thank you, Ferruccio, for the very nice talk. Hope you see you soon somewhere else.
Thank you for the invitation. Thank you. Have a nice day. Ciao.
Ciao.